beneath your feet right now. The earth is on fire. Before we go any further, if you want a brand new earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Not the kind of fire you can see, not the kind that flickers and fades. This fire has been burning for 4.5 billion years, deep inside the rock and metal at the center of our world. It burns slowly, steadily, quietly, and it has never once gone out. If you could somehow float above the earth and look down, you'd see a blue and white marble drifting in the dark, oceans catching the light, clouds swirling in slow, wide spirals. The surface looks still from up there. It looks peaceful, but that surface is just a thin shell, like the skin on a piece of fruit, and beneath it, something vast and ancient is always moving. The Earth's core sits roughly 3,900 miles below where you're lying right now. That's about the same distance as flying from New York to London, and then halfway back again. At that depth, the temperature reaches somewhere between 9,000 and 10,800 degrees Fahrenheit. That is hotter than the surface of the sun. The outer layers of our star burn at around 10,000 degrees Fahrenheit, and the center of the Earth matches that almost exactly. Scientists have confirmed this through the study of seismic waves, the ripples that earthquakes send through the planet's body, like sound moving through a bell. That heat doesn't just sit still. It moves. It rises very slowly through thousands of miles of solid and semi-liquid rock. It pushes upward the way warm air rises in a room. And as it moves, it carries energy with it. Energy that has been stored inside this planet since before the first ocean formed, since before the first raindrop ever fell. The amount of heat flowing out of the earth at any given moment is staggering. Scientists estimate that roughly 47 terawatts of heat energy escape from the Earth's interior every single year. 1 terawatt is 1 trillion watts. To put that in some kind of human scale, the entire world's electricity use in a year is only about 2.5 terawatts. The Earth releases nearly 20 times that much heat continuously just by existing. It breathes warmth the way a sleeping animal breathes air. Most of that heat escapes so slowly and so evenly that we never feel it. The ground under your feet releases only about 60 milliwatts of heat per square meter, far too gentle for human skin to detect. But in certain places, the Earth's heat finds a crack, a weakness, a thin spot in the crust, and there it rises fast. It boils water. It melts rock. It shoots steam into the sky. It reminds us that the quiet ground we walk on is not as solid or as cool as it seems. Those places are windows. They are places where the deep interior of the planet reaches up and touches the surface world. Volcanoes, geysers, hot springs, fumaroles, those hissing vents in the ground that breathe steam and sulfur. Each one is a message from the center of the earth, sent upward through miles of stone. And here is something that quietly connects everything in this story. The heat inside the earth does not just warm the ground. It drives the movement of the great tectonic plates, the massive sections of crust that carry the continents on their backs. Those plates move because heat rises beneath them and pulls them along. The mountains, the oceans, the continents themselves are all shaped by the slow movement of heat from the core outward. The world you see when you look out, a window, was sculpted by the same fire that burns beneath your feet tonight. This episode is about that fire. It's about where it came from, how it moves, what it does, and what we as humans have learned to do with it. It's about the remarkable fact that the ground itself is a source of clean, endless energy, if only we know where to look and how to listen. So settle in. Let your breathing slow. The story of Earth's heat is one of the oldest stories this planet has to tell. It started before life existed here. It will continue long after we are gone. And tonight, quietly, it is still unfolding, just a few miles below the place where you rest your head. To understand why Earth is so hot inside, we have to go back, way back. About 4.5 billion years ago, there was no Earth at all. There was only a vast cloud of gas and dust drifting through space, left over from an ancient star that had died long before. That cloud began to pull together. Gravity drew the dust and gas inward, slowly at first, then faster and faster. Bits of rock and ice collided. They stuck together. They grew. Over millions of years, these collisions built up the young Earth, piece by piece. Every single impact released energy. Every crash sent heat rippling through the growing rock. The planet was being born, and being born is a violent thing. Picture a ball of rock, the size of a city, slamming into the early Earth at tens of thousands of miles per hour. Then picture that happening again and again, millions of times. All that energy had nowhere to go. It sank into the rock and stayed there. Scientists call this process accretion, which simply means the slow gathering of material into a larger body. The heat from accretion alone was enough to melt the entire planet. For a time, Earth was a world of liquid rock. The surface glowed a deep, angry orange, like a coal pulled fresh from a fire. There were no oceans then, no continents, no air worth breathing, just a churning ocean of molten stone stretching from one horizon to the other. The heat from those early collisions is still inside the planet right now. Some of it has never escaped. Earth has been slowly releasing that original warmth for 4.5 billion years, and it still hasn't finished. But the collisions weren't the only source of heat. As the planet melted, something remarkable happened. The heavier elements, mostly iron and nickel, began to sink toward the center. The lighter rock floated upward. This process is called differentiation, which means the sorting of materials by weight. It's the same reason oil floats on water. Heavy things sink, light things rise. That sinking took enormous effort. Gravity pulled the dense iron downward through thousands of miles of molten rock. All that movement generated friction. Friction makes heat. Scientists estimate that the process of differentiation may have released as much energy as 100 million powerful earthquakes happening all at once. That heat joined everything already stored inside the planet, building up a reservoir of warmth so deep and so vast that nothing on the surface can fully cool it. So Earth carries two kinds of original heat. The first came from the violence of its birth. All those collisions piling up energy over millions of years. The second came from its own settling, the long, slow sorting of heavy from light. Together, they gave the planet a core that reached temperatures of perhaps 7,000 degrees Celsius, which is roughly as hot as the surface of the sun. That number is almost too large to hold in the mind. But it's real. It's down there right now, beneath your feet, beneath the ocean floors, beneath every mountain and every plain. There's one more piece to this story, and it changes everything. Even after the collisions stopped and the planet began to cool, a new source of heat switched on. Certain elements locked inside the rock, elements like uranium and thorium and potassium, began to decay. Radioactive decay is the slow process by which unstable atoms break apart and release energy as heat. These elements act like tiny furnaces buried in the rock, burning not with fire, but with the quiet energy of atomic change. This radioactive heat is still being produced today. It accounts for roughly half of all the heat currently flowing out of Earth's interior. The other half is that ancient warmth, the leftover glow from the planet's violent formation. Both sources work together, keeping the interior hot, keeping the rock in the mantle moving, keeping the plates of the crust drifting slowly across the surface. Earth is not cooling quickly. The planet loses heat from its surface at a very slow rate, and the radioactive elements inside keep adding more. Scientists believe Earth will remain geologically active, meaning its interior will keep driving volcanoes and earthquakes and the slow drift of continents for billions of years to come. The heat that was born in chaos, in the crash and tumble of a forming solar system, has become the steady, quiet engine of a living world. It warms the ground beneath every forest. It drives every hot spring. It powers every volcano. It all began with a cloud of dust and the pull of gravity, and it hasn't stopped since. Beneath your feet right now, the earth is built in layers. Think of it like a hard-boiled egg. There's a thin shell on the outside. Beneath that shell is a thick white layer, and at the very center sits a small, dense yolk. Earth works the same way. Only the layers are made of rock and metal, and they hold more heat than anything on the surface could ever match. The outermost layer is called the crust. It's the part we live on. The ground under your house, the floor of the ocean, the stone beneath every mountain range, all of that is crust. On land, the crust runs about 25 to 70 kilometers deep. Under the ocean, it's much thinner, sometimes only 5 kilometers from the seafloor to the layer below. That might sound like a lot, but compared to the full size of Earth, the crust is almost nothing. It's like the skin of an apple wrapped around everything else. Below the crust lies the mantle. The mantle is the thickest layer of Earth, stretching nearly 2,900 kilometers down. It's made of rock, but not the kind of rock you'd pick up on a hiking trail. This rock is under enormous pressure, squeezed so hard from all sides that it behaves almost like a very slow liquid. Over millions of years, the mantle moves. It creeps and flows in huge, slow currents, carrying heat upward from the deep interior toward the surface. This movement is called convection, the same process that stirs a pot of soup on a stove. Hot material rises, cools slightly, then sinks back down, only to be heated again. The mantle has been doing this for billions of years without stopping. Deeper still, past the mantle, sits the outer core. This is where things get truly extraordinary. The outer core is made almost entirely of liquid iron and nickel, metals so hot they've melted completely. The temperature here reaches somewhere between 4,000 and 5,000 degrees Celsius. That's roughly as hot as the surface of the sun. The outer core is about 2,200 kilometers thick, and it flows in slow, churning currents. Those currents are what generate Earth's magnetic field, the invisible force that makes compass needles point north and shields the planet from harmful radiation streaming in from space. Without the outer core, life on the surface would look very different. At the very center of everything sits the inner core. It's a solid ball of iron and nickel, roughly 1,200 kilometers across, about the size of the moon. The inner core is actually hotter than the outer core, reaching temperatures close to 5,000 to 6,000 degrees Celsius. So why is it solid when the layer around it is liquid? Pressure. The weight of the entire planet pressing down from every direction is so immense that the metal cannot melt, no matter how hot it gets. The inner core holds its shape under conditions that would be impossible to recreate anywhere on Earth's surface. These 4 layers, the crust, the mantle, the outer core, and the inner core, didn't form all at once. They sorted themselves out slowly, over hundreds of millions of years, during a process scientists call differentiation. Early in Earth's history, the planet was largely molten, a churning ball of liquid rock and metal. Gradually, the heaviest materials, iron and nickel, sank toward the center. The lighter rocky materials floated upward and eventually cooled into the crust. It was a slow, quiet sorting, driven entirely by gravity. What makes this layered structure so important for geothermal energy is the way heat moves through it. The inner core radiates heat outward into the outer core. The outer core passes that heat into the mantle. The mantle slowly carries it upward toward the crust, and in certain places where the crust is thin or cracked, that heat reaches the surface. Every hot spring, every geyser, every volcanic vent is a window into this deep structure. Each one is a place where the heat from those inner layers has found a path to the world above. The 4 layers of Earth are not separate, isolated things. They work together constantly, exchanging heat, generating magnetic fields, driving the slow drift of continents across the surface. Each layer depends on the others. The inner core's heat feeds the outer core's motion. The outer core's motion protects the surface. The mantle's slow flow shapes the crust above it. Everything connects. Everything passes something along to the next layer. The way a flame passes warmth to whatever it touches. The earth is not still. It never has been. Even now, deep below the quiet ground, the layers are moving and the heat is rising. Deep inside the rocks beneath your feet, something quiet is happening. It has been happening for billions of years. Tiny, invisible processes inside certain minerals are slowly releasing heat, not from fire, not from pressure, but from the atoms themselves breaking apart. This is radioactive decay. It sounds dramatic, but it is actually one of the gentlest, most patient forces in nature. Certain atoms are unstable. They carry too much energy inside their cores, so they release that energy bit by bit over millions and millions of years. And as they do, they warm the rock around them, main elements doing this work are uranium, thorium, and potassium-40. These three elements sit inside common rocks. Granite, in particular, holds a good amount of all three. Granite is that speckled gray and pink rock you might have seen on a kitchen counter or a mountain cliff face. It looks solid and still, but inside it, atoms are quietly, constantly releasing heat. Scientists estimate that roughly half of all the heat flowing out of Earth right now comes from this radioactive decay. The other half is leftover warmth from when Earth first formed. That ancient heat from the violent collisions of rock and gas that built our planet. But the radioactive portion is remarkable because it is self-renewing in a sense. These elements decay slowly enough that they are still releasing meaningful heat today, after 4.5 billion years. Uranium is one of the slowest. Uranium, the most common form, has a half-life of about 4.5 billion years. A half-life is the time it takes for half of a given amount of an element to decay. That means the uranium inside Earth's rocks is only now reaching its halfway point. It will keep releasing heat for billions of years more. Earth is not cooling as fast as a simple rock in space would cool, because it carries its own internal fuel. Thorium is even slower. Its most common form has a half-life of about 14 billion years, longer than the current age of the universe. Thorium is also more abundant in Earth's crust than uranium. Together, these two elements form a slow, steady engine buried in the rock. Now here is where the story opens up to something bigger. These elements did not form on Earth. They could not have. Elements as heavy as uranium and thorium are not made in ordinary stars. Our sun, for all its power, cannot forge them. They require something far more violent. The death of a massive star in a supernova explosion, or the collision of two neutron stars, the dense, collapsed cores of dead stars, crashing into each other at tremendous speed. When stars that are much larger than our sun reach the end of their lives, they explode with unimaginable force. In those final moments, the energy is so extreme that it creates heavy elements that could not exist anywhere else. Uranium, thorium, gold, platinum. These elements scatter outward into space in the explosion's wake. Some of that scattered material, drifting through the galaxy over millions of years, eventually became part of the cloud of gas and dust that collapsed to form our solar system. The rocks that built Earth carried those heavy elements inside them. And so, when Earth formed, it inherited a supply of radioactive fuel, a gift from long-dead stars, the heat you feel rising from a hot spring, or the steam venting from a geothermal power plant traces back, in part, to those ancient stellar explosions. The warmth inside Earth is, in a very real sense, starlight stored in stone. Potassium-40 adds another layer to this picture. Potassium is a common element in Earth's crust. It shows up in many rocks and minerals. Most potassium is stable, but a small fraction, about 1 atom in every 10,000, is the radioactive form, potassium-40. It decays into argon and calcium, releasing heat as it goes. Its half-life is about 1.25 billion years, making it faster acting than uranium or thorium, and a meaningful contributor to Earth's internal warmth. These three elements work together across deep time. None of them are rare in the grand scheme of the planet. They are woven into the ordinary rock of the crust and mantle. Every mountain, every ocean floor, every quiet stretch of plains sits above rock that is, at this very moment, producing a small but real amount of heat. It is easy to think of rocks as cold and inert, but they are not. They carry within them the memory of dying stars and the slow, patient energy of atoms finding their way to rest. The ground beneath you is alive with that ancient warmth, still glowing after billions of years. Heat does not sit still. Even deep inside solid rock, where there is no wind, no water, no movement you could ever see, heat is always on the move. It travels slowly, quietly, through the densest stone on Earth. And understanding how it moves helps us understand why our planet is still warm after 4.5 billion years. The first way heat moves through rock is called conduction. Conduction is the slow transfer of heat from one particle to the next, like a chain of tiny handshakes passing warmth along. Hold one end of a metal spoon over a flame and the far end grows warm. That is conduction. Rock does the same thing, just much more slowly. Stone is not a great conductor. It passes heat along at a crawl. But the earth has so much heat and so much time that even this slow process shapes everything above it. Different rocks conduct heat at different rates. Dense, heavy rocks like granite carry heat better than lighter. Porous rocks full of tiny air pockets. This means the heat rising from Earth's core does not travel evenly. It moves faster through some rock and slower through others. The result is a planet where some regions of the crust run hotter than others, where the ground in one valley might be warm to the touch, while the next ridge overstays cool. The uneven nature of rock itself creates the uneven heat we feel at the surface. But conduction alone is not enough to explain how heat moves through the deep earth. Below the crust in the mantle, something else takes over. The mantle is that thick layer of hot rock sitting between the thin outer crust and the iron core far below. The rock there is so hot and under such enormous pressure that it behaves almost like a very slow, very thick liquid. It does not flow like water. It creeps. Over millions of years, it moves in great looping currents called convection cells. Convection works like this. Hot rock near the core becomes slightly less dense as it heats up. It rises very slowly toward the surface. As it rises, it cools a little. Cooler rock is denser, so it sinks back down. Then it heats up again and rises again. This loop, rising and sinking, has been turning inside the earth for billions of years. It is one of the great engines of our planet. These slow convection currents are what moves the tectonic plates, the massive sections of crust that carry the continents. The same force that carries heat upward through the mantle is the same force that once split a single supercontinent into the 7 we know today. There is a third way heat moves, and it works differently from the other 2. Radiation allows heat to travel as invisible waves of energy without needing any material to pass through at all. Inside the earth, radiation plays a smaller role than conduction or convection, but it still matters. Deep in the core, where temperatures reach over 5,000 degrees Celsius, roughly the same temperature as the surface of the sun. Heat radiates outward in all directions, pressing against the rock above it like a slow, constant breath. Pressure plays its own role in all of this. As rock sinks deeper into the earth, the weight of everything above it squeezes it tighter and tighter. This pressure raises the temperature at which rock melts. So even though the deep mantle is incredibly hot, much of it stays solid simply because the pressure is so great. It is a careful balance. Too much heat and the rock melts into magma. Too much pressure and it stays locked solid. Most of the mantle exists right at the edge of that balance, creeping and shifting, but never fully melting. These three forces, conduction, convection, and radiation, work together constantly. They have been working together since the Earth first formed. They carry heat from the blazing core outward through thousands of kilometers of rock, delivering it slowly to the surface. They drive the movement of continents. They fuel volcanoes. They warm the ground beneath your feet on a cold morning. Every hot spring, every steaming vent, every geothermal power plant on Earth owes its existence to these quiet, invisible forces moving heat through stone. It is easy to think of rock as something fixed and permanent, something that simply sits there, cold and still. But rock is alive with movement, alive with heat, alive with forces that have been at work since long before the first living thing ever drew breath on this planet. The stone beneath us is never truly at rest. Deep beneath your feet right now, the earth is glowing with heat. Most of that heat stays locked far below, moving so slowly through solid rock that it barely reaches us. But in certain places on this planet, the heat doesn't wait. It finds a way up. And when it does, the results are some of the most striking things you'll ever see. The thin outer shell of the earth, the crust, ranges in thickness from about 3 miles under the ocean floor to nearly 40 miles beneath the tallest mountain ranges. That might sound thick, but compared to the full depth of the earth, which stretches nearly 4,000 miles to the center, the crust is thinner than the skin of an apple. In a few special places, that thin shell cracks, stretches, or wears down even further. Heat from below rises through those weak spots like warmth, rising through a thin blanket. Volcanoes are the most dramatic of these places. There are roughly 1,500 potentially active volcanoes on Earth's surface today. About 500 of those have erupted in recorded human history. When a volcano erupts, it's not just rock and ash coming up. It's heat that has been building for thousands of years, finally breaking free. The lava pouring from a volcano can reach temperatures of 2,000 degrees Fahrenheit. That's hot enough to melt steel. A single large eruption can release more energy in hours than an entire country uses in a year. But volcanoes are only the loudest way Earth's heat reaches the surface. There are quieter ones too. Along the ocean floor, where the tectonic plates, the giant, slow-moving slabs of rock that make up Earth's outer shell, pull apart from each other. Magma wells up constantly. These underwater ridges stretch for nearly 40,000 miles across the ocean floor. That's longer than the distance around the entire Earth at the equator. Geologists call this the mid-ocean ridge system, and it is the longest mountain range on the planet. Almost all of it sits hidden beneath miles of dark water, glowing faintly with heat. On land, the places where Earth's heat comes closest to the surface are called geothermal zones. The word geothermal simply means heat from the earth. These zones often sit near the edges of tectonic plates, where the crust is thinner and more active. Iceland is one of the most famous examples. The entire island sits directly on top of the mid-Atlantic ridge, where two plates are slowly pulling apart. The ground there is so warm in places that you can feel it through the soles of your shoes. Iceland gets more than half of its total energy from geothermal sources because the heat is simply that close to the surface. The Yellowstone region in the western United States is another place where Earth's heat sits unusually close. Beneath Yellowstone lies a massive reservoir of hot rock, fed by a column of heat rising from deep in the mantle. Scientists call this a hotspot. The heat has pushed the ground up into a broad dome, roughly 40 miles wide. In some parts of Yellowstone, the ground temperature just a few feet below the surface reaches nearly 200 degrees Fahrenheit. The soil in those areas is too hot to touch. To understand how rare and remarkable these places are, consider this. If you spread all of Earth's geothermal hot zones out across the planet's surface, they would cover less than 1% of the total land area. 1%. The rest of the land sits on crust thick enough and cool enough that the deep heat never quite makes it up. But that 1% holds some of the most active, most alive, most visually stunning landscapes on Earth. Steaming ground, boiling pools of brilliant blue and orange, vents hissing white clouds into cold air. The colors in geothermal pools are not just beautiful. They're a map of temperature. The hottest water near the vent itself often runs clear or pale blue. As the water cools toward the edges, it turns yellow, then orange, then deep red and brown. Those colors come from heat-loving microbes, tiny living things that thrive in water. Most creatures couldn't survive for a second. The cooler the water, the more types of life it supports, and the richer the color becomes. Every steaming vent, every boiling pool, every glowing lava field is a window, a small, rare opening in the thin shell of a planet that is, from its very center to its surface, alive with heat. The Earth doesn't keep all of that warmth hidden. In these places, it shares it. Quietly, steadily, and in colors you won't forget. Imagine standing at the edge of a wide, flat basin in the middle of Wyoming. The ground around you is pale and chalky, crusted with minerals left behind by thousands of years of boiling water. The air smells faintly of sulfur, like a struck match that hasn't quite gone out. Steam rises in soft white columns all around you. And then, without warning, the earth beneath your feet begins to rumble. A column of boiling water shoots straight up into the cold morning air. It climbs higher than a 10-story building. It holds there for a moment, trembling and roaring, and then it falls back down in a curtain of white mist. You've just watched Old Faithful do what it has done for centuries. You've just watched the earth breathe. Geysers are one of the rarest things on this planet. There are only about 1,000 of them in the entire world. Most of them are clustered in just 5 places. Yellowstone in the United States, Kamchatka in Russia, Chile, New Zealand, and Iceland. To find a geyser, you need a very specific set of conditions, all in the same place at the same time. First, you need a source of intense heat close to the surface. Second, you need a supply of groundwater, the rainwater and snowmelt that seeps slowly down through cracks in the rock. Third, and most important, you need a narrow underground channel shaped in just the right way. That channel acts like a pipe. It traps the water. It holds the pressure. And when the pressure finally wins, the geyser erupts. Here's what happens inside that pipe. Water near the bottom sits directly above a pocket of superheated rock. It gets hotter and hotter, but the weight of all the water above it keeps it from boiling. Water under pressure needs a much higher temperature to boil than water in an open pot. So the heat keeps building. The water keeps straining. And then, when the temperature finally crosses a threshold the pressure can't hold, the water at the top of the column flashes into steam. That steam expands instantly. It blasts the water above it upward with tremendous force. The whole column erupts at once. Old Faithful at Yellowstone erupts roughly every 44 to 125 minutes. Scientists can predict its next eruption based on how long the last one lasted. A longer eruption empties more water from the underground chamber, so the next one takes longer to build back up. It's a rhythm, a slow geological pulse that has been beating long before any human being stood there to watch it. The water that shoots out of a geyser is extraordinarily hot. At Yellowstone, geyser water often reaches around 204 degrees Fahrenheit, or about 95 degrees Celsius, just below the boiling point at that elevation. When it hits the open air, some of it flashes instantly into steam. The rest falls back to the ground as scalding droplets, collecting in shallow pools that shimmer with color. Those colors are not just beautiful. They tell a story. The brilliant blues and greens near the center of a hot spring or geyser pool come from the water itself, which absorbs red light and reflects blue. But the rings of orange, yellow, and brown around the edges come from something alive. Colonies of heat-loving bacteria called thermophiles, meaning heat lovers, grow in thick mats along the cooler margins of the water. Each color band marks a different temperature zone. Each zone holds a different community of microscopic life. The whole thing looks like a painting, and it is one drawn slowly by living things over thousands of years. Yellowstone sits on top of one of the largest volcanic hotspots on Earth. The magma chamber beneath it, a vast underground reservoir of partially molten rock, sits only a few miles below the surface in some places. That closeness is what makes Yellowstone so alive with geothermal activity. The park contains more than half of all the geysers on Earth. More than 500 active geysers erupt within its borders. Walking through Yellowstone is like walking across the skin of something vast and breathing. The ground there is not stable in the way most ground is. It rises and falls slightly over years as the magma chamber below shifts and swells. In some places, the crust is thin enough that the heat below warms the soil just a few inches down. In winter, snow melts in strange circular patches where the ground runs warm. The earth is not cold and dead beneath your feet. It is alive with stored heat, with pressure, with slow and patient energy that has been building since before the first human eye ever opened to see it. Somewhere deep beneath the surface of the earth, water moves through cracks in ancient rock. It seeps down slowly, pulled by gravity, finding its way through stone that has been there for millions of years. And then it meets the heat. The rock far below is hot enough to warm that water to temperatures far above boiling. The water rises back up, carrying that heat with it, and where it finally reaches the surface, something remarkable waits. Hot springs are pools of naturally heated water that form where this rising water meets the open air. They come in every size. Some are small and still, barely bigger than a bathtub. Their surfaces smooth and glassy. Others are wide and steaming, surrounded by rings of color that look almost painted on. The grand prismatic spring in Yellowstone National Park is one of the largest hot springs in the world. It stretches nearly 370 feet across, and its colors shift from deep blue at the center to vivid orange and red at the edges. Those colors are not from the water itself. They come from living things. The rings of color around hot springs are made by microbes called thermophiles, which means heat lovers. These are tiny single-celled organisms that thrive in conditions that would kill almost anything else. Near the center of a hot spring, where temperatures can reach close to 200 degrees Fahrenheit, almost nothing survives. But moving outward, as the water cools just slightly, different species of thermophiles take hold. Each one prefers a slightly different temperature. The result is a series of rings, each one a different color, each one home to a different community of life. Orange, yellow, green, brown, each band is its own world. Scientists first studied these microbes seriously in the 1960s, when a researcher named Thomas Brock collected samples from Yellowstone's hot springs. He found bacteria living in water that was nearly boiling. At the time, most scientists believed nothing could survive such heat. Brock's discovery changed that completely. One of the microbes he found, called Thermus aquaticus, turned out to be extraordinarily useful. The heat-stable proteins inside it became the foundation for a laboratory technique called PCR, which allows scientists to copy tiny amounts of DNA very quickly. That technique is now used in medicine, criminal investigations, and disease research around the world. Life found in a hot spring helped transform modern science. Beneath the surface of a hot spring, the water tells a long story. Rain falls on the land and soaks into the ground. It travels downward through layers of rock, sometimes for thousands of years, moving so slowly it barely seems to move at all. Deep underground, it absorbs minerals from the rock around it. Silica, calcium, sulfur, iron, all of these dissolve into the water as it heats. When the water finally rises and reaches the surface, it carries those minerals with it. Over time, the minerals deposit around the edges of the spring, building up slowly into strange and beautiful formations. The pale white terraces of Mammoth Hot Springs in Yellowstone are made this way, layer by layer, over centuries. The water in some hot springs is not just warm, it is rich with dissolved gases too. Hydrogen sulfide gives some springs their sharp, sulfurous smell. carbon dioxide bubbles up through others. These gases come from deep within the earth, carried upward by the same forces that move the water. In some places, the gas content is high enough that the water fizzes gently, like something carbonated. The earth is exhaling slowly and steadily through every crack and pool and spring. Not all hot springs are dramatic. Many are quiet places, tucked into forests or hidden in mountain valleys. In Iceland, small hot springs dot the countryside, and people have bathed in them for over 1,000 years. The warmth is gentle and steady, fed by the volcanic heat beneath the island. In Japan, natural hot spring baths called onsen have been part of daily life for centuries. The culture around them is careful and calm. People come to rest, to be still, to let the earth's warmth move through them. There is something deeply settling about the idea that the ground beneath us holds this warmth. That water falling as rain can travel down through rock, gather heat from the planet's interior, and return to the surface carrying that heat like a gift. The earth does not keep it all. It shares it slowly through every spring and pool and steaming vent. And wherever that warm water surfaces, life finds a way to meet it. Even in the most extreme conditions, in water nearly hot enough to boil, something is alive. Something is thriving. The heat that drives the whole planet turns out to be generous enough to share. Picture a ring drawn around the entire Pacific Ocean. Not a small ring. A ring that stretches 40,000 kilometers, nearly the full distance around the Earth. Along this ring, about 90% of the world's earthquakes happen. About 75% of all active volcanoes sit right along its edge. This is the Ring of Fire, and it pulses with a rhythm that has been beating for hundreds of millions of years. The Ring of Fire exists because of the way Earth's outer shell is broken into pieces. These pieces, called tectonic plates, move slowly across the surface of the planet. They drift on top of the mantle, that thick, hot layer of rock beneath the crust. Where two plates meet, something dramatic almost always happens. One plate often slides beneath the other in a process called subduction. The plate that goes under sinks deep into the mantle, where the heat is immense. That sinking plate carries water with it, locked inside its rocks. When that water gets hot enough, it changes the melting point of the surrounding rock. The rock melts, magma forms, and that magma pushes upward, looking for any crack or weakness in the crust above. That upward push is what creates the volcanoes of the Ring of Fire. Countries like Japan, the Philippines, Indonesia, Chile, and the United States all sit along this arc. They all share this same deep, restless energy beneath their feet. The volcanoes don't erupt on a fixed schedule. They breathe in long, slow cycles that can last decades or even centuries. A volcano might sleep quietly for 300 years, then wake with tremendous force. The energy was never gone. It was simply building. This cycle of pressure and release is one of the most important rhythms on the planet. Magma rises slowly through the crust, collecting in chambers, large underground spaces where molten rock gathers and waits. Pressure builds over time as more magma pushes in from below. Eventually, that pressure finds a way out. Sometimes it escapes gradually through slow lava flows. Sometimes it releases all at once in a violent eruption. Either way, the heat from deep inside the earth is making its way to the surface. The planet is exhaling. Along the Ring of Fire, this exhale brings enormous amounts of geothermal energy close to the surface. The crust here is thinner than in most other places. The heat doesn't have as far to travel. Countries that sit on the Ring of Fire have some of the richest geothermal resources on Earth. The same forces that make these regions prone to earthquakes and eruptions also give them access to a nearly endless source of clean, steady heat rising from below. Japan sits directly on the Ring of Fire, and the Japanese have understood the power of this heat for a very long time. The country has thousands of natural hot springs called onsen. These springs are fed by the same volcanic energy that occasionally shakes the ground. The water that fills them has traveled through hot rock deep underground, picking up minerals and warmth before rising to the surface. It's the same cycle, playing out gently in a quiet mountain valley or a small coastal town. Iceland tells a similar story. It sits on the mid-Atlantic ridge, where two tectonic plates are slowly pulling apart rather than colliding. As the plates separate, hot material from the mantle wells up to fill the gap. This makes Iceland one of the most volcanically active places on Earth. The island is essentially being built in real time. New rock forms as lava cools. The land itself is growing slowly, year by year, and all of that volcanic activity means heat is constantly available just below the surface. The rhythm of the ring of fire is not chaotic, even if it sometimes feels that way. It follows the deeper rhythm of the planet's interior, the slow churning of the mantle, the gradual movement of plates, the steady rise of heat from the core. These cycles operate on timescales that are hard to imagine. A single cycle of plate movement can take tens of millions of years to complete. Yet, within that vast sweep of time, smaller rhythms nest inside larger ones. Eruption cycles, earthquake swarms, seasons of volcanic quiet followed by seasons of activity. Everything connects back to the same source. The heat at the center of the earth drives the movement of the plates. The movement of the plates creates the ring of fire. The ring of fire shapes the land, the oceans, the climate, and the lives of billions of people who live along its arc. From the deepest part of the core to the surface of a steaming hot spring, it is all one continuous, slow breathing system. Deep beneath your feet, the ground gets warmer with every step down. Not by much at first, but the deeper you go, the more you feel it. On average, the temperature rises about 25 to 30 degrees Celsius for every kilometer you drill into the Earth's crust. Scientists call this the geothermal gradient, the steady climb in heat as you move toward the planet's core. It's a slow burn that never stops. To reach that heat, we drill. And drilling into the earth is one of the most remarkable things human beings have ever learned to do. The tools we use are called drill rigs. They look like tall steel towers rising above the ground, sometimes 10 stories high or more. A long steel pipe runs down through the rig, spinning slowly, grinding through rock layer by layer. The tip of the drill is called a drill bit, and it's often made from some of the hardest materials we know: tungsten carbide or industrial diamond. These materials can chew through solid granite and basalt, the dense dark rock that makes up much of the Earth's crust. Progress is slow. A drill might cut through just a few meters of rock in a single hour. Some wells take weeks or months to complete. The deeper the well, the harder the work. Rock pressure increases with depth. Heat increases. The drill pipe itself can warp and bend under the stress. Engineers monitor everything constantly. The temperature of the returning rock chips, the pressure inside the well, the angle of the drill. Most geothermal wells reach depths of 1 to 3 kilometers. That's deep enough to find rock temperatures between 150 and 300 degrees Celsius in the right locations. In places like Iceland, where volcanic activity brings heat close to the surface, useful temperatures appear at much shallower depths. In other places, like the middle of a stable continent, you might need to drill 5 or 6 kilometers to find the same warmth. The rock itself tells a story as you drill through it. Near the surface, you find softer sedimentary rock, the kind built up over millions of years from sand, mud, and ancient sea floors. Deeper down, the rock changes. It becomes harder, older, more compressed. You pass through layers that formed hundreds of millions of years ago, long before any dinosaur walked the earth. Each layer is a page in a very long book. Drilling doesn't happen in isolation. The wells we sink into the earth sit within a neighborhood of other systems. Underground water moves through cracks and pores in the rock, carrying heat from one place to another. These natural water systems, called aquifers, which are layers of rock that hold and carry water, often become the target of geothermal drilling. When hot water already exists underground, the job becomes much simpler. You drill down, tap the aquifer, and let the hot water rise to the surface on its own. Pressure from below pushes it up. This is exactly what happens in the Paris Basin in France, where geothermal wells have been drawing hot water from deep aquifers since the 1960s. The water comes up at around 57 degrees Celsius, not hot enough to generate electricity, but perfect for heating homes and buildings. Thousands of apartments in the Paris suburbs stay warm in winter thanks to water pulled from rock that formed during the age of dinosaurs. The wells we drill also interact with the geology around them in ways that require careful attention. Drilling can sometimes open new cracks in rock or connect existing ones. Water injected into the ground to extract heat can shift the stress on underground faults. The fractures in rock where tectonic plates meet or grind. In some cases, this has triggered small earthquakes. They're usually minor, barely felt at the surface. But engineers study the local geology carefully before choosing a drill site, mapping the faults nearby, and monitoring seismic activity throughout the process. The relationship between a geothermal well and its surroundings is always a two-way exchange. The earth gives up its heat. The water carries it upward. The rock shifts and settles in response. Engineers watch and adjust. Nothing about this process happens in a vacuum. The drill site, the aquifer, the fault lines, the surface equipment, they all form one connected system, each part responding to the others. It's a quiet kind of partnership between human ingenuity and the slow, patient heat of a planet that has been warming itself from within for 4.5 billion years. We reach down, the earth reaches back, and somewhere in that exchange, warmth rises to the surface and finds its way into the world above. Deep beneath the surface of Iceland, engineers have drilled into rock so hot it would melt most metals. The temperatures down there reach above 400 degrees Celsius. That's not just hot. That's hotter than the inside of a kitchen, oven set to its absolute maximum, then doubled. And yet, humans have found a way to reach into that heat and pull electricity out of it. Geothermal power plants are some of the most remarkable machines on Earth. They don't burn anything. They don't need wind or sunlight. They simply reach down into the ground and let the planet do the work it has been doing for 4.5 billion years. The most powerful type is called a dry steam plant. These are the oldest kind, and they work only in very special places where steam rises directly from cracks in the ground. The steam shoots up through pipes, spins a turbine, and generates electricity. It sounds almost too simple. The The world's largest dry steam field sits at the Geysers in Northern California. It has been producing power since 1960, making it one of the longest-running geothermal facilities on the planet. At its peak, the Geysers could power a city the size of San Francisco all on its own. Most geothermal plants, though, work a little differently. They use what's called a flash steam system. Hot water deep underground is under enormous pressure, which keeps it liquid even at temperatures well above boiling. When engineers pump that water up toward the surface, the pressure drops fast. The water flashes instantly into steam. That burst of steam drives a turbine. The leftover water is then pumped back down into the earth to be heated again. The whole cycle repeats quietly and continuously, day and night. There is a third type called a binary cycle plant. These are the most clever of all. They use water that isn't quite hot enough to flash into steam on its own. Instead, that hot water passes next to a second fluid, one with a much lower boiling point. The heat transfers from the water into this second fluid, which boils, becomes vapor, and spins the turbine. The original water never even touches the turbine. It goes straight back underground. Binary cycle plants can run on water as cool as 57 degrees Celsius, which means they can operate in places where the other types simply couldn't. This is what makes geothermal energy so extreme in its range. It works in volcanic Iceland, where the ground practically boils on its own. It also works in quiet, flat regions where the heat is subtle and deep. The technology has stretched to fit the planet's enormous variety. The record for the deepest geothermal well ever drilled belongs to a project in Iceland called IDDP, the Iceland Deep Drilling Project. In 2017, that drill reached a depth of about 4.5 kilometers and hit something extraordinary. It struck what scientists call a magma intrusion, a pocket of molten rock that had pushed up close to the surface. The temperatures at the bottom of that well reached 427 degrees Celsius. The pressure was so intense that the water down there existed in a strange state called supercritical fluid, something between liquid and gas that carries far more energy than regular steam. A single well in that condition could theoretically produce 10 times the electricity of a normal geothermal well. 10 times. From one hole in the ground. The efficiency of geothermal plants is also remarkable when you compare them to other energy sources. A well-designed geothermal plant can run at full capacity more than 90% of the time. Solar panels work only when the sun shines. Wind turbines need wind, but the Earth's heat is always there, steady and patient, pushing upward through the rock, no matter the season or the weather. Geothermal plants also take up very little land. A single plant can generate enormous amounts of power from a footprint smaller than many farms. The pipes go down, not out. The energy comes from below, not from acres of panels or rows of towers stretching across a hillside. And when the steam is done spinning the turbines, it doesn't disappear into pollution. Most of it condenses back into water and returns to the ground. Some plants release a small puff of water vapor into the air, which drifts away harmlessly. The whole system is a loop fed by heat that has been building inside the Earth since before life existed on its surface. The planet offers this energy freely. It has been doing so for longer than any mountain, any ocean, any living thing. Geothermal plants are simply the moment when humans finally learned to listen. Some countries have learned to listen to the ground beneath them. They've learned to hear its slow, steady warmth. And a handful of places on Earth have built their entire way of life around that heat. Iceland is the most famous of them. This small island nation sits directly on the mid-Atlantic ridge, the place where two of Earth's great tectonic plates, the massive slabs of rock that make up the crust, are slowly pulling apart. That pulling creates cracks, and through those cracks, heat rises freely. Today, Iceland gets nearly all of its electricity from renewable sources. Geothermal energy alone powers around 30% of the country's electricity and heats roughly 90% of its homes. Not with gas, not with coal, with the quiet warmth of the earth itself. Walk through Reykjavik, Iceland's capital city, on a cold winter morning. The air is sharp and pale. Snow sits on the rooftops. But The sidewalks are warm underfoot in many places, heated by pipes carrying geothermal water just below the surface. The city pipes hot water directly from underground reservoirs into homes, schools, and swimming pools. Those outdoor pools stay open all year, steaming gently in the winter air, full of people floating in water that the earth heated on its own. Kenya tells a different kind of story. It sits far from any tectonic boundary, but it lies along the East African Rift, a place where the African continent is slowly tearing itself apart. That process takes millions of years, but right now it creates a long chain of volcanic activity and underground heat. Kenya's Alkaria geothermal field, located in the Great Rift Valley, is one of the largest geothermal power stations in the world. It provides nearly half of Kenya's electricity. For a country still building its energy future, that's a remarkable thing. The Earth is doing a great deal of the work. The Philippines is another quiet leader. This archipelago, a chain of more than 7,000 islands, sits along one of the most volcanically active zones on the planet. The country gets around 17% of its electricity from geothermal sources, making it one of the top geothermal producers on Earth. The steam that rises from deep wells on the island of Leyte powers entire cities. It comes from the same volcanic forces that built those islands in the first place. The same heat that once shook the ground now keeps the lights on. New Zealand draws about 17% of its electricity from geothermal energy as well. The Werricke Power Station, built in the 1950s near the town of Taupo, was one of the first geothermal plants in the world to generate electricity on a large scale. It sits in a region of intense volcanic activity, surrounded by bubbling mud pools and hissing steam vents. Scientists there have studied the ground for decades. They've learned how the underground water moves, how the pressure shifts, how the heat behaves over time. That knowledge now helps geothermal engineers all over the world. El Salvador, a small country in Central America, gets around 25% of its electricity from geothermal sources. It sits on the Pacific Ring of Fire, that great arc of volcanic activity that that circles the Pacific Ocean. The volcanoes that once threatened the land now quietly power it. There's something almost poetic about that. The same forces that built the mountains are now lighting the homes in their shadow. The United States produces more raw geothermal electricity than any other country in the world. Most of that power comes from a single place, the Geysers, a vast geothermal field in Northern California. It's the largest complex of geothermal power plants on Earth. Dozens of plants sit across the hills there, drawing steam from wells drilled deep into hot rock. That steam spins turbines. Those turbines generate electricity for hundreds of thousands of homes across Northern California. The land above looks like quiet, golden hills. Below, it hums with heat. What's striking about all these countries is how different they are. A cold island in the North Atlantic, a rift valley in East Africa, a volcanic archipelago in Southeast Asia. They share no border, no language, no culture, but they share something deeper. They all live on ground that breathes. They've all learned to work with the earth rather than against it. Each one found a way to take what the planet offers freely and turn it into something useful. The earth doesn't run out of this heat on any human timescale. It has been building it for 4.5 billion years. These countries are simply borrowing a little warmth from something vast and ancient and endlessly generous. Long before anyone built a power plant or drilled a well, people noticed something simple and strange. The ground near certain springs stayed warm even in deep winter. The water that bubbled up from the earth held heat that the cold air could not touch. For thousands of years, that warmth was a mystery. Then, slowly, people started asking why. The Romans were among the first to put that mystery to work. They built elaborate bathhouses over natural hot springs across their empire, from Italy to Britain to North Africa. These weren't just places to wash. They were gathering places, social centers, heated entirely by the earth itself. The Romans didn't fully understand where the heat came from, but they understood that it was reliable. It never ran out. It was simply there, rising from below, steady and generous. In Iceland, the story goes back even further in spirit. though the formal use of geothermal heat for homes came much later. The Norse settlers who arrived on that volcanic island more than 1,000 years ago found hot springs everywhere. They used them for bathing and cooking. The land itself seemed alive with warmth. But it wasn't until the early 20th century that Icelanders began to think about piping that heat directly into their homes. In 1930, a small town in Iceland called Reykjavik took a bold step. Engineers drilled wells into the hot rock beneath the city and pumped the heated water through pipes directly into houses. It was one of the first district heating systems in the world. A district heating system is a network of pipes that carries hot water from a central source to many buildings at once, like a giant underground radiator. Reykjavik's system worked beautifully. The city grew. The system grew with it. Today, nearly the entire city of Reykjavik runs on geothermal heat for its homes and buildings. The idea spread slowly. In the United States, the city of Boise, Idaho holds a special place in this history. Boise sits above a large geothermal reservoir, a deep underground pool of naturally heated water. As far back as 1892, the city began piping that hot water to homes and businesses through wooden pipes. That makes Boise one of the oldest geothermal district heating systems in the United States. The wooden pipes were eventually replaced with modern materials, but the system still runs today, more than a century later. What these early engineers discovered was a concept called direct use. Direct use means taking the Earth's heat and applying it straight to a task, without first converting it to electricity. Heating a home, warming a greenhouse, drying fish or lumber, heating the water in a swimming pool. All of these are forms of direct use. They're simple, efficient, and remarkably effective. The heat moves from the ground to the building with very little wasted in between. The science behind direct use became clearer through the 19th and 20th centuries as geologists began mapping underground heat sources more carefully. They learned that certain rock formations hold hot water under pressure, like a sealed pot on a stove. When you drill into those formations, the water rises. It carries its heat with it. You can capture that heat, use it, and then return the cooled water back into the ground to be warmed again. The system feeds itself, cycling slowly through the rock like breath through a living body. France became a leader in this approach during the 1960s and 1970s. Engineers in the Paris Basin, a wide underground rock formation beneath northern France, drilled into deep aquifers, which are layers of rock that hold large amounts of water. They found water warm enough to heat homes. By the 1980s, thousands of apartments in and around Paris were being heated this way. It was quiet, invisible, and clean. Residents simply turned on their heat, and the earth provided. What these pioneers discovered, from the Roman bath builders to the Icelandic engineers to the geologists of France, was that the earth is not stingy with its warmth. It offers heat freely, steadily, without smoke or flame. You only have to know where to look and how to listen. The knowledge came in pieces across centuries, passed from one curious mind to the next, each discovery built on the last. Each city that piped hot water into its homes showed the next city that it was possible. The Romans didn't know about radioactive decay or convection currents deep in the mantle, but they knew warmth when they felt it, and they reached down and held on. That instinct to find the earth's heat and bring it home turns out to have been exactly right. Here is something that surprises almost everyone who hears it. No matter where you live in a cold city, a frozen tundra, a windswept plain, the ground just a few feet below your feet is warm. Not hot, not burning, but steady and mild, like a hand pressed gently against the earth. Just 10 feet down, the soil holds a temperature somewhere between 50 and 60 degrees Fahrenheit in most parts of the world. That warmth doesn't come from the sun. It comes from below. The sun heats the surface, yes, but that heat fades quickly as you go deeper. What takes over is the slow, ancient heat rising from Earth's interior. Even in places where the air above is bitterly cold, the ground below holds its warmth like a secret. This is why animals like groundhogs and foxes dig burrows. They figured this out long before humans did. A burrow just a few feet deep stays warmer in winter and cooler in summer than the air above. The earth itself becomes a shelter. That steady underground temperature is called the geothermal gradient zone, the layer where Earth's deep heat and the sun's surface heat find a kind of balance. Now here is where it gets genuinely strange. That stable temperature underground is almost the same everywhere on Earth, regardless of the climate above. A spot in northern Canada and a spot in southern France might have wildly different winters. But dig down 10 feet in both places, and the temperature is remarkably close. The ground doesn't care about the weather. It has its own slow, deep warmth that runs on a completely different clock. Scientists use this fact in a surprising way. Heat pumps, devices that move warmth from one place to another, can pull that underground warmth into a building in winter. In summer, they push the building's heat back down into the cool ground. The earth acts like a giant battery, storing and releasing energy across the seasons. These systems use very little electricity because they're not creating heat. They're just moving it. The ground does most of the work. Here is another thing that catches people off guard. The deeper you drill, the hotter it gets, but not at the same rate everywhere. In most places, the temperature rises about 25 to 30 degrees Celsius for every kilometer you go down. That's called the geothermal gradient. But in some places, that number is much higher. Near volcanic regions, the temperature can jump 80 or even 100 degrees Celsius per kilometer. The crust there is thinner, and the heat below pushes closer to the surface. What this means is that the ground is not a flat, uniform thing. It has hot spots and cool spots, thick patches and thin ones. Some places sit above ancient, cooled rock that holds very little heat. Others sit above zones where magma, molten rock, lurks just a few kilometers down. The difference between those two places can be enormous, even if they look exactly the same from above. There's a detail about rock that most people never think about. Different rocks conduct heat at different speeds. Granite, the hard, pale rock that makes up much of the continental crust, is a poor conductor. It holds heat slowly and releases it slowly. But basalt, the dark rock that forms under oceans and in volcanic regions, conducts heat much better. So the same amount of heat rising from Earth's core can feel very different depending on what kind of rock it passes through. The rock itself shapes how the heat moves. Scientists have also found something unexpected in very deep mines. Workers in gold mines in South Africa, some of the deepest in the world, descend more than 2 miles underground. Down there, the rock temperature can reach 60 degrees Celsius, hot enough to be dangerous. Massive cooling systems run constantly just to keep the air breathable. The miners are working inside the Earth's natural heat, and the Earth pushes back. That image stays with you. Miles underground, surrounded by ancient rock glowing with slow heat, workers carving through a planet that is still very much alive. The heat isn't dramatic. It doesn't roar or flash. It just presses in, steady and patient, the way it has for billions of years. The ground beneath your feet right now is doing the same thing. Quietly, constantly. Whether you're standing on a sidewalk in a busy city or a field in the middle of nowhere, the earth below you is holding its warmth. It has been doing this since before the first life crawled out of the sea. It will keep doing it long after we're gone. There is something deeply calming about that. Far beneath the surface of the ocean, where no sunlight has ever reached, the seafloor opens up. Cracks split the rock. Superheated water shoots upward in dark, billowing clouds. These are hydrothermal vents, and they are one of the most astonishing places on Earth. The water coming out of these vents can reach temperatures above 700 degrees Fahrenheit. That is hot enough to melt lead. And yet, somehow, this water does not boil. The pressure of the deep ocean, miles and miles of seawater pressing down from above, keeps it liquid. Pressure changes everything down there. These vents form where tectonic plates, the giant, slow-moving slabs that make up Earth's outer shell, pull apart or press together along the ocean floor. Cold seawater seeps down through cracks in the rock. It sinks deep, gets close to the hot magma below, and heats up fast. Then it rises back up, carrying dissolved minerals with it. When that superheated water meets the near-freezing ocean water above, those minerals solidify instantly. They stack up, layer by layer, forming tall chimneys of rock rising from the seafloor. Some of these chimneys grow taller than a 5-story building. The water that pours from these chimneys looks like smoke. When the minerals are dark, iron sulfide mostly, the vent is called a black smoker. When the minerals are lighter, the vent is called a white smoker. Both kinds are pouring Earth's inner heat directly into the cold, dark ocean. They are a direct line from the planet's core to the sea. Now here is where the connections become truly wonderful. For most of Earth's living things, the sun is everything. Sunlight feeds plants. Plants feed animals. The whole web of life on the surface runs on solar energy. But down at the hydrothermal vents, the sun does not exist. It is completely dark, and yet life is everywhere. Scientists discovered hydrothermal vents in 1977 near the Galapagos Islands in the Pacific Ocean. They expected to find a barren, empty seafloor. Instead, they found a riot of life. Giant tube worms, some growing up to 8 feet long, clustered around the vents in thick white colonies. Ghostly white crabs picked their way across the rock. Clams the size of dinner plates lay open in the warm water. It was unlike anything anyone had ever seen. The key to all this life is a process called chemosynthesis. In chemosynthesis, certain bacteria use the chemicals pouring out of the vents, especially hydrogen sulfide, a gas that smells like rotten eggs, as fuel. They turn those chemicals into energy, the same way plants turn sunlight into energy. These bacteria are the base of the entire food chain down there. Everything else eats them, or eats something that eats them. Life found a way to run on Earth's heat instead of the sun's light. This discovery changed how scientists think about life itself. Before 1977, most researchers assumed life required sunlight. The vents proved otherwise. Now scientists look at other worlds with new eyes. Europa, one of Jupiter's moons, has a vast ocean buried under miles of ice. That ocean never sees sunlight. But Europa's rocky seafloor may be warmed by tidal forces, the gravitational squeezing caused by Jupiter's enormous pull. If hydrothermal vents exist on Europa, life might exist there too. Earth's deep ocean vents opened a door to the entire universe. Back on our own planet, the vents do more than support life. They shape the chemistry of the whole ocean. The minerals they release, iron, manganese, copper, zinc, spread out through the water in slow, invisible clouds. These minerals eventually become part of the seafloor sediment. Over millions of years, they get folded back into the rock by the movement of the tectonic plates. Earth recycles its own minerals endlessly through heat and pressure and time. The ocean and the deep earth are not separate systems. They breathe together. Cold water goes down. Hot water comes up. Minerals move from rock to sea and back again. The heat at the center of the planet reaches all the way to the creatures living in the dark. And those creatures are part of a cycle that has been running for billions of years. There is something deeply calming about this. Even in the coldest, darkest, most remote corners of the planet, warmth finds a way through. Earth's heat does not stay locked inside. It rises. It spreads. It feeds life in places where life has no business existing at all. And somewhere on the pitch-black seafloor right now, a tube worm is swaying gently in the warm current rising from below. Alive because of the heat inside our world. Deep in volcanic regions, the ground itself seems to breathe. Steam rises from cracks in the earth. Gases drift upward through pale yellow rock. These openings are called fumaroles, and they are one of the strangest and most beautiful features our planet produces. A fumarole is simply a vent in the Earth's surface where hot gases escape. The gases come from magma, the molten rock sitting far below. As that magma heats the groundwater and surrounding rock, gases like steam, carbon dioxide, and sulfur dioxide push upward and find any crack they can. The result looks almost alive. Thin columns of white vapor curl into the cool air above. The ground around a fumarole is often stained bright yellow or orange from sulfur deposits left behind as the gases pass through. Fumaroles are not permanent. That is one of the most important things to understand about them. They change constantly, over years and over centuries. A fumarole that vents steam today might go quiet in a decade if the underground heat source shifts. A new crack might open somewhere nearby and start venting instead. The ground in volcanic regions is always rearranging itself at a pace too slow for us to watch, but fast enough to measure over a human lifetime. Some fumaroles are called solfataras, a name that comes from an old Italian word for sulfur. These vents release particularly sulfur-rich gases and are found in places like the Campi Flegrei region near Naples, Italy, where an enormous underground volcanic system keeps the ground warm and restless. Scientists watch these areas carefully because changes in fumarole activity can signal shifts in the magma below. More gas, hotter temperatures, new cracks. These are the Earth speaking in a language geologists have spent generations learning to read. Mud pots are something else entirely. They form when acidic gases rise through the ground and break down the surrounding rock into a soft, wet clay. Then steam and gas bubble up through that clay, creating pools of thick, gurgling mud. The mud pots at Yellowstone National Park in the United States are some of the most famous in the world. They sit in shallow depressions in the ground, their gray and brown surfaces slowly churning, popping, and plopping in a rhythm that feels almost musical. The colors can be striking: pale gray, rust red, creamy white, depending on the minerals dissolved in the mud. The temperature of a mud pot can reach close to the boiling point of water. But because the mud is so thick, it doesn't splash violently. It moves slowly, heavily, like something dreaming. Scientists believe the consistency of a mud pot changes with the seasons. In wet months, more water mixes in and the mud becomes thinner and more fluid. In dry months, it thickens. The same vent, the same heat, but a different face depending on what the sky has been doing. This is one of the quieter truths about geothermal features. They are not fixed. They respond to rainfall, to earthquakes, to the slow migration of heat underground. A mud pot that was thin and bubbling in spring might be nearly solid by late summer. A fumarole that vented loudly for 50 years might go silent after a small tremor shifts the rock around it. The surface features we see are just the visible edge of a system that is always in motion below. There are also features called hot ground areas, where no visible vent exists at all. The soil itself is warm to the touch. In some places in Iceland and New Zealand, the ground temperature just a few inches below the surface stays warm enough to cook an egg. Farmers in parts of Iceland have used this warmth for centuries to heat soil and extend the growing season for crops. The earth gives heat freely, and people have always found ways to accept the gift. All of these features, fumaroles, mud pots, hot ground, solfataras, are connected to the same deep engine. They are different expressions of the same underground heat, shaped by local rock, local water, and local chemistry into wildly different forms. One hillside might have a fumarole venting pale steam. Just a few hundred meters away, a mud pot gurgles quietly in a hollow. Nearby, the ground is simply warm underfoot, with no visible sign of what lies below. The earth does not express itself the same way twice. It finds new paths, new forms, new surfaces to touch. And all of it is changing, slowly and steadily, the way everything on this planet changes. Not in a single moment, but across years and centuries, one small shift at a time. There is a glow that comes from the earth itself, not the reflected light of the sun, not the cold shimmer of the moon. This is something older and deeper. When lava spills from a volcanic vent and crawls slowly across dark rock, it carries a color that feels almost alive. Bright orange at the edges, white hot at the center. The light it gives off is the same light that has been building inside this planet for 4.5 billion years, finally finding a way out. That glow tells a story about cost. Everything in nature has one. Geothermal energy is often called a free resource, and in many ways it is. The heat is already there. It was placed inside the earth long before the first human being ever walked across it. We don't burn anything to make it. We don't dig up ancient forests compressed into coal. We don't pump up buried oceans of oil. We simply reach down and borrow what the planet is already giving away. But borrowing still has a price. When engineers drill deep into the earth to pull up steam or hot water, they sometimes release gases that have been trapped underground for a very long time. One of those gases is hydrogen sulfide. It has a sharp, unpleasant smell, like something gone wrong. Geothermal power plants must carefully capture and manage these gases so they don't drift into the surrounding air. Modern plants do this well, but it takes effort and it matters. There is also a gas called carbon dioxide that rises from geothermal wells. The amount is small. Compared to a coal plant producing the same amount of electricity, a geothermal plant releases roughly 18 times less carbon dioxide. That difference is enormous. Still, the number is not zero. The Earth's own breath carries a little carbon, and when we open a path for that breath to escape faster than it would on its own, we add a small amount to the air above. Light helps us see this clearly. Scientists use satellites to study the infrared light, the heat light that human eyes can't see, rising from geothermal fields around the world. From space, these zones glow with a warmth that stands out against cooler ground. The Taupo volcanic zone in New Zealand shines in those invisible wavelengths. So does the Salton Sea in California and the great geothermal fields of Iceland. Satellites can measure how much heat a region is releasing and whether human activity is changing that release. In some places, pulling too much hot water from the ground has caused the land to sink very slowly. This process is called subsidence, which means the ground settles downward as the fluid that once supported it is removed. In Werrikei, New Zealand, one of the oldest geothermal fields in the world, parts of the land have sunk by several meters over decades of heavy use. The change is gradual, but it reshapes the surface in ways that can affect roads, buildings, and the flow of rivers. There is a visual poetry to this. The same heat that lights the inside of a volcano, that turns water to steam and drives a turbine, that warms a home in Iceland through a long, dark winter, also leaves a mark. A slow, quiet, geological mark. The earth keeps a kind of record. Water is part of the cost too. Many geothermal plants use water to cool their systems, and in dry regions, that water is precious. Engineers have worked hard to design plants that re-inject the used water back into the ground, completing a loop. The water goes down, heats up, comes back as steam, does its work, cools down, and returns to the earth again. When this loop works well, it's a remarkably clean exchange. The colors of a geothermal field at night are something to imagine. The soft orange glow of a power plant's lights reflected in the rising steam. The pale blue shimmer of a silica-rich hot spring, that mineral giving the water an almost unreal color. The dark shapes of cooling towers against a sky full of stars. It looks like a place where the earth is breathing. And it is. The cost of geothermal energy, when measured honestly, is small. Far smaller than the fuels that came before it. The gases are manageable. The land changes are local and slow. The water can be returned. What the earth gives up in heat, it has been giving up since long before we arrived. We are simply learning to stand in the right place and receive it. The glow was always there. We are only now learning to read its light. Deep beneath a quiet field in the middle of a continent, engineers are listening. Not with their ears exactly, but with sensors buried in the ground, picking up the faintest tremors in the rock. The earth is always moving, always shifting, always speaking in vibrations too low for human hearing. And now we've learned to listen. This is the world of enhanced geothermal systems, and it begins with a simple problem. Most of the heat locked inside our planet sits in dry rock. There's no water nearby to carry that heat upward. No natural spring, no geyser, no steaming vent. Just hot stone, sitting quietly miles below the surface, holding enormous amounts of energy that we couldn't reach. So engineers found a way to bring water to the heat themselves. The process works like this. Workers drill 2 deep holes down into hot, dry rock, sometimes 3 miles down or more. They pump water into the first hole under high pressure. That water cracks through the rock, finding tiny pathways and fractures, spreading through the stone like roots through soil. Then the water absorbs the heat from the rock around it. It travels through those cracks and rises back up through the second hole, now superheated and full of energy. At the surface, that heat gets converted into electricity. Scientists call this an enhanced geothermal system, or EGS for short. The word enhanced means we're not waiting for nature to provide the water. we're creating the conditions ourselves. But here's where the listening comes in. When engineers pump water into rock under high pressure, the rock cracks, and cracking rock makes sound. Not the kind of sound you'd hear standing in a field above. These are seismic waves, tiny vibrations that travel through the earth the way ripples travel across a still pond. Sensors buried in the ground detect these waves, and computers turn them into data. Engineers use that data like a map, tracking exactly where the water is moving, how far the cracks have spread, and whether the rock is behaving the way they expected. It's a form of underground listening that feels almost like holding a stethoscope to the Earth's chest. The challenge is keeping those cracks small and controlled. When rock fractures too aggressively, the vibrations can grow strong enough to be felt at the surface as small earthquakes. Scientists call this induced seismicity, which means earthquakes caused by human activity rather than natural tectonic movement. In a few early EGS projects, small quakes were felt by people living nearby, and some projects were paused or shut down as a result. Researchers have spent years studying how to manage this. They've learned that slower water injection at lower pressures produces smaller and more controlled fractures. The rock still cracks, the water still flows, but the vibrations stay small. The listening never stops. Sensors monitor the ground around the clock, and if the tremors start growing, engineers can ease off the pressure immediately. There's something remarkable about this back and forth between human engineering and the living rock. The earth pushes back, and we adjust. We learn its language, one tremor at a time. The potential locked inside EGS technology is genuinely staggering. Hot, dry rock exists almost everywhere on Earth, not just in volcanic regions or near tectonic boundaries. A 2006 report from the Massachusetts Institute of Technology estimated that EGS could theoretically supply more than 2,000 times the total energy the United States uses each year. That heat is already there, already waiting, stored in rock that has been slowly warming for billions of years. The United States, Australia, France, Germany, and South Korea have all run EGS research projects. The technology is still developing, still being refined. But the direction is clear. Every year, the listening gets better. The sensors grow more sensitive. The models that predict how rock will crack become more accurate. Engineers are learning to have a conversation with the earth rather than simply drilling into it and hoping for the best. There's a kind of quiet poetry in this. We live on a planet that hums with heat, that vibrates with slow, deep energy, that has been generating warmth since before the first oceans formed. For most of human history, we sat on top of that energy without knowing it was there. Now we're pressing our instruments to the ground, reading the signals, learning the rhythms. The earth has always been speaking. We're only just beginning to understand what it's saying. And in that slow, careful listening, in those sensors buried in dark rock miles below a quiet field, there is something that feels less like engineering and more like a conversation between a species and the world that made it. Earth is not the only world with heat burning inside it. Across our solar system, other planets and moons carry their own inner fires. Some of those fires burn hotter than anything we have here. Some burn in ways that still surprise scientists today. Take Jupiter's moon Io. It is roughly the same size as our own moon. But Io is the most volcanically active body in the entire solar system. Scientists have counted over 400 active volcanoes on its surface. Some of those volcanoes shoot plumes of sulfur dioxide, gas more than 300 miles into space. The surface glows orange and yellow and white, painted by sulfur compounds that pool and freeze and melt again in a constant cycle. The heat inside Io does not come from radioactive decay the way Earth's does. It comes from something called tidal flexing. Jupiter's gravity is enormous. It pulls on Io with tremendous force. But two other large moons, Europa and Ganymede, also pull on Io from different directions. Io gets squeezed and stretched as it orbits, over and over, like a ball of clay being kneaded by invisible hands. That squeezing creates friction deep inside the moon. Friction creates heat. The math behind this process is elegant in its simplicity. The gravitational forces involved are so precisely calculated that that scientists can predict exactly how much heat Io generates from this squeezing alone. It produces roughly 100 trillion watts of power this way. That is about twice the total heat flowing out of Earth's entire surface. Europa, that same neighboring moon, tells a quieter story. Its surface is covered in smooth white ice, cracked with long brown lines like the surface of a broken eggshell. Beneath that ice, scientists believe, lies a liquid ocean. The evidence for this ocean is strong. Europa's surface shows signs of movement, of ice shifting and refreezing over something fluid below. That same tidal flexing that scorches Io warms Europa more gently. The heat is enough to keep water liquid in a place that sits nearly 500 million miles from the sun. The ocean beneath Europa's ice may be twice as deep as any ocean on Earth. Enceladus, a small moon of Saturn, does something even more dramatic. It vents water vapor and ice particles directly into space from cracks near its south pole. These geysers shoot material hundreds of miles above the surface. Scientists have flown spacecraft through those plumes and tasted what's inside. They found water, salts, silica particles, and organic molecules. The basic building blocks that chemistry needs to get interesting. The heat driving those geysers comes from the same tidal squeezing that warms Io and Europa. Saturn's gravity flexes Enceladus, and that flexing keeps a liquid ocean warm beneath its frozen shell. The numbers here are worth sitting with for a moment. Enceladus is only about 300 miles across. It is smaller than the state of Texas, and yet this tiny frozen world generates enough internal heat to maintain a liquid ocean, drive active geysers, and release complex chemistry into space. Size does not determine heat. The right gravitational relationships can warm even the smallest world. Mars carries a different kind of inner heat. Its core has cooled considerably over billions of years. Mars is smaller than Earth, so it lost its heat faster. The way a small stone cools faster than a large boulder. Scientists believe Mars may still have some geothermal activity deep underground, though its surface shows no active volcanoes today. NASA's InSight lander, which which sat on the Martian surface and listened for Marsquawks, detected faint seismic rumbles that suggest the interior is not entirely still. The planet's heat has faded, but it has not gone completely dark. Even Venus, our closest planetary neighbor, holds heat deep inside. Venus is almost exactly Earth's size, which means it likely formed with a similar amount of radioactive material in its rocks. Scientists believe Venus may still have active volcanoes, though the thick clouds that wrap the planet make it hard to see clearly. Recent data from spacecraft suggests fresh lava flows on the surface, perhaps only a few years old. The pattern across all these worlds is the same simple rule. Heat comes from two sources: the energy locked inside radioactive atoms and the energy created by gravity squeezing and pulling. Every world that has either of those things carries warmth inside it. The universe runs on these two quiet forces, and they show up everywhere you look, from the orange fires of Io to the hidden ocean beneath Europa's ice to the faint trembling of a cooling Mars. The same physics that warms your feet on a heated floor warms the hearts of worlds across the solar system. Long before anyone drilled a well or built a power plant, people found the hot springs. They gathered at the edges of steaming pools. They watched the water rise from the earth, warm and clear, smelling of minerals and deep stone. And they knew, without any science to explain it, that something powerful lived below. The Maori people of New Zealand have lived near geothermal springs for over 1,000 years. The region called Rotorua sits on one of the most active geothermal fields on Earth. The ground there hisses and bubbles. Mud pools churn like slow, gray soup. The Maori used the hot springs to cook food, to bathe, to heal. They built their lives around the heat. To them, the earth's warmth was not a resource to be used up. It was a living presence to be respected. In Japan, the tradition of onsen, which means natural hot spring bathing, goes back at least 2,000 years. The Japanese islands sit along the Pacific Ring of Fire, where tectonic plates grind and shift and push heat toward the surface. There are over 3,000 hot spring resorts in Japan today. Millions of people visit them every year. The water comes up rich with minerals like sulfur, calcium, and magnesium. These minerals have real effects on the skin and muscles. The heat opens blood vessels and helps the body relax. Ancient people did not need a doctor to tell them this. They felt it. The Romans built elaborate bathhouses over geothermal springs across their empire. The city of Bath, in what is now England, sits above a spring that pushes out about 1 million liters of hot water every single day. The Romans called it Aquisules, meaning the waters of the goddess Sulis. They built temples beside the pools. They threw offerings into the water. They believed the heat came from the gods. In a way, they were not wrong to feel that something immense was at work. Native American tribes across the western United States treated hot springs as sacred ground. The Shoshone people called the hot springs near what is now Thermopolis, Wyoming, a gift from the Great Spirit. When the land was eventually purchased in 1896, the Shoshone insisted that part of the spring remain free and open to all people forever. That agreement still holds today. You can still bathe there at no cost, just as the Shoshone always believed you should. What all these cultures understood in their own ways was something that modern science now confirms. The heat is not infinite. The system is delicate. Hot springs exist because a precise set of conditions lines up perfectly. Water must seep down through cracks in the rock. It must reach depths where the earth is hot enough to warm it. The rock must be porous enough to let the water move, but solid enough to hold pressure. The water must find a path back to the surface. Change any one of those conditions, and the spring goes quiet. Some springs have gone quiet. Overuse of geothermal water in Rotorua during the 20th century caused many springs and geysers to slow and stop. The water table dropped. The pressure fell. The earth stopped speaking in those places. New Zealand's government eventually stepped in, limiting how much water could be drawn from the ground. Slowly, some of the springs recovered. The lesson was clear. Even the Earth's deep heat, ancient and vast as it is, responds to what we do at the surface. This is the fragile balance that ancient peoples seemed to sense without being told. The earth gives heat freely, but it gives it through systems that took millions of years to form. The cracks and channels and aquifers, which are underground layers of water-soaked rock, are not replaceable on any human timescale. If we drain them too fast, or pollute them, or seal them off, they do not come back in a lifetime. They may not come back in 10 lifetimes. There is something worth sitting with in the fact that the oldest human relationship with geothermal energy was one of reverence. People gathered at the springs not to extract everything they could, but to be near something larger than themselves. They cooked their food, they healed their bodies, they offered thanks, and then they left the water running. The earth has been warm since before the first living thing crawled across its surface. That warmth has never asked anything of us. It simply rises, steady and patient, through stone and water, toward the open air. The ancient peoples who sat beside those steaming pools were closer to understanding that gift than they perhaps knew. There are places on this planet where the water is near boiling, where the ground hisses and steams, where most living things would die within seconds. And yet, in those same places, life is thriving. Scientists call them extremophiles. That word simply means organisms that love extreme conditions. They don't just survive in heat, they need it. Without the warmth of geothermal energy, they wouldn't exist at all. Some of the most remarkable are called thermophiles, which means heat lovers. These are tiny single-celled organisms, often bacteria or archaea, that live in hot springs and geothermal pools around the world. The bright orange and yellow rings you see around the edges of Yellowstone's grand prismatic spring are not paint or minerals. They are living mats of thermophilic bacteria, millions of them layered together, feeding on the heat and the chemicals rising from below. The colors shift as the temperature changes. The hottest water near the center glows a deep blue. Moving outward, where the water cools slightly, the bacteria begin to appear. First yellow, then orange, then deep red at the cooler edges. Each color is a different species, each one perfectly tuned to its own narrow band of temperature. It's one of the most vivid natural displays on Earth, and it's alive. What scientists still don't fully understand is how these organisms manage it. Proteins in most living things fall apart at high temperatures. Heat breaks the bonds that hold them together. But thermophiles have proteins that stay stable even in near boiling water. Researchers have been studying this for decades, and the exact mechanisms are still not completely clear. The answers, when they come, may help us design medicines, industrial enzymes, and materials that work in extreme heat. One discovery changed science forever. In the 1960s, a microbiologist named Thomas Brock found a bacterium living in a Yellowstone hot spring at temperatures above 70 degrees Celsius, which is around 160 degrees Fahrenheit. That organism, called Thermus aquaticus, contained an enzyme that could copy DNA at high temperatures without breaking down. That enzyme became the foundation of a technique called PCR, which scientists now use to detect viruses, solve crimes, and sequence the human genome. A single heat-loving microbe from a geothermal pool quietly changed the course of modern medicine. And yet, scientists believe there are thousands more species in geothermal environments that haven't been studied yet. Many haven't even been named. The hot springs of Iceland, the volcanic vents of New Zealand, the geothermal fields of East Africa, all hold microbial communities that researchers are only beginning to explore. Each one could contain something entirely new. The deep ocean vents are perhaps the greatest mystery of all. Hydrothermal vents on the ocean floor support entire ecosystems that get no energy from sunlight. Giant tube worms, some as long as 2 meters, cluster around the vents in pale white and deep red. Ghostly white crabs pick through the mineral deposits. Shrimp swarm in the warm, chemical-rich water. None of these animals could exist without the heat rising from below the seafloor. The tube worms are especially puzzling. They have no mouth, no stomach, no digestive system at all. Instead, they host billions of bacteria inside their bodies, and those bacteria convert the chemicals from the vent into energy the worm can use. Scientists call this chemosynthesis, which is the process of making energy from chemicals rather than sunlight. It was only discovered in 1977 when the first deep-sea vent was found. Before that, scientists assumed all life on Earth ultimately depended on the sun. That assumption turned out to be wrong. What we still don't know is how widespread these vent ecosystems are. The deep ocean floor is vast and largely unmapped. New vents are found regularly, and each one seems to host its own unique community of species. Some researchers believe the deep ocean may hold more undiscovered species than all the rainforests on land combined. That is not a confirmed number. It's an estimate, but it suggests the scale of what remains unknown. There's also a deeper question that scientists are quietly working on. If life can thrive on chemical energy from geothermal heat, with no sunlight at all, then life might exist in similar environments elsewhere in the solar system. Europa, one of Jupiter's moons, has a liquid ocean beneath its icy surface, kept warm by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, shoots geothermal plumes of water vapor into space. Both worlds could, in theory, support chemosynthetic life near their seafloors. We don't know yet. The honest answer is that we simply don't know. But the creatures living around Earth's geothermal vents have already shown us something extraordinary. Life finds a way, even in the dark, even in the heat, even where no sunlight ever reaches. Geothermal energy doesn't just power our homes. It shapes the very ground beneath our feet, slowly and quietly, over millions of years. Think about Yellowstone. That vast, steaming plateau in the American West sits on top of one of the largest volcanic hot spots on Earth. Over the last 2 million years, the heat rising from below has pushed the land upward, cracked it open, and filled it with color. The bright orange and yellow rings around Yellowstone's hot pools come from heat-loving microbes that live nowhere else on Earth. The ground itself is a record of what heat can do, written in stone and steam and mineral-stained rock. Geothermal heat is one of the slowest sculptors on the planet. It works across time spans that are almost impossible to imagine. In Iceland, the mid-Atlantic ridge, the long crack in the ocean floor, where two of Earth's great tectonic plates pull apart, runs right through the middle of the island. Iceland is actually getting wider. Every year, the eastern and western halves of the island drift about 2 centimeters farther apart. The heat rising from below keeps the gap open and keeps the island alive with volcanoes and hot springs. In 1,000,000 years, Iceland will look very different from the island it is today. Farther out in time, the changes grow even more dramatic. Scientists believe that in roughly 250 million years, the continents will come together again. Earth has done this before. The supercontinent Pangaea, that single vast landmass where all of today's continents were once joined, broke apart about 175 million years ago. Before Pangaea, there were other supercontinents. The process runs in a slow cycle, driven in large part by the movement of heat from deep inside the Earth. The mantle, that thick layer of hot rock between the crust and the core, churns in huge, slow loops called convection currents. These currents drag the plates of the crust along with them, like objects floating on the surface of a very slow river. When the next supercontinent forms, geothermal activity will reshape the land in ways we can barely picture. New mountain ranges will rise where plates collide. New rift valleys will open where plates pull apart. New hot springs and volcanoes will dot landscapes that don't exist yet. The heat inside the Earth will keep doing what it has always done, pressing upward, finding cracks, building and breaking and building again. But the Earth's inner heat is not endless. It is very slowly fading. The radioactive elements deep inside the planet, uranium, thorium, potassium, are the source of much of that heat. They release energy as they decay, as they slowly break down into simpler elements over billions of years. Over time, there will be less and less of them. Scientists estimate that the Earth's interior will cool significantly over the next several billion years. The mantle will grow stiffer. The tectonic plates may slow and eventually stop moving altogether. Mars may show us what that future looks like. Mars is smaller than Earth, and it cooled much faster. Today, Mars has no active tectonic plates. Its volcanoes are silent. Its surface is still and cold. The great volcano Olympus Mons, the tallest mountain in the solar system, nearly 3 times the height of Mount Everest formed because Mars had no moving plates to carry the crust away from its hot spot. The heat just kept pushing up through the same spot, building and building. Earth's moving plates spread that energy around. Mars held it in one place until it went quiet. In about 5 billion years, our sun will expand into a red giant star, growing so large it may swallow the inner planets entirely. Long before that happens, Earth's surface will become too hot for liquid water. But deep underground, in the rock, the heat from Earth's core will still be there. Some scientists believe that even as the surface burns, the deep subsurface could remain a refuge for heat-loving microbes for a long time to come. The story of geothermal energy is the story of time itself. It is a story written in slow motion, in the language of rock and heat and pressure. Every geyser that erupts, every hot spring that steams in the cold morning air, every volcanic island rising from the sea. These are chapters in a story that started 4.5 billion years ago and won't end for billions more. The Earth is still becoming something. It has always been becoming something, and the heat at its heart is the quiet engine driving all of it forward. There is a fire that has never gone out. It started before the earth existed, before the oceans filled, before the first breath of oxygen touched the air. Long before any living thing opened its eyes to the light, this heat was already here, buried deep in the dark, waiting. That same fire still burns today. Right now, beneath your feet, beneath the city, or the field, or the quiet forest outside your window, the earth holds an enormous store of heat. Scientists estimate that the total thermal energy, the heat energy stored inside our planet, is roughly 10 billion times the amount of energy the entire human race uses in a single year. That number is almost too large to hold in your mind, but it's there, steady, patient, enormous. For most of human history, we barely touched it. We soaked in hot springs. We warmed our hands near volcanic vents. We watched geysers shoot columns of white steam into cold mountain air and felt something ancient and powerful moving beneath us. But we didn't know how to use it. Not really. That's changing now. Engineers and scientists around the world are working to unlock geothermal energy, the heat from inside the earth, as one of the great clean power sources of the future. Unlike solar panels, it doesn't need the sun to shine. Unlike wind turbines, it doesn't need the wind to blow. The Earth's heat is there every hour of every day, in every season, in almost every place on the planet. It is one of the most reliable sources of energy that exists. Right now, geothermal power plants generate electricity in more than 30 countries. Iceland gets nearly all of its electricity and heat from the ground beneath it. Kenya draws almost half of its national power from geothermal sources. The United States produces more geothermal electricity than any other country, most of it from a region in California called the Geysers, where steam fields have been generating power since 1960. But those places sit on top of easy heat. They're near volcanoes or tectonic plate boundaries, where the Earth's warmth rises close to the surface. Most of the world doesn't have that. Most places have to dig deeper. That's exactly what a new technology called enhanced geothermal systems is trying to do. Engineers drill deep wells into hot, dry rock, pump water down, let it absorb the heat, and bring it back up as steam to drive turbines and make electricity. Early projects are already running in places like Utah and Finland and Australia. The technology is still young, but the potential is staggering. Some estimates suggest that enhanced geothermal systems could eventually supply more than 10 times the current electricity needs of the entire United States, using only a small fraction of the heat available in the rock below. Think about what that means. No smoke, no carbon dioxide poured into the sky, no fuel that runs out, just the slow, steady warmth of a planet that has been holding this heat for 4.5 billion years. The Earth formed from a swirling cloud of gas and dust around a young star. Gravity pulled that cloud together. The pressure of all that colliding material generated enormous heat. Radioactive elements locked inside the rock began to decay, releasing more heat still. That process has been running ever since, deep in the mantle and the core. A slow nuclear fire that has no need for oxygen and no plan to stop. We are in a very real sense, the children of that fire. The iron in our blood was forged in the heart of a dying star. The calcium in our bones was scattered across space in an ancient explosion. And the warmth beneath our feet is the leftover heat of a solar system being born. We carry the universe inside us, and the universe, in a way, is still warming us from below. Geothermal energy isn't just a power source. It's a reminder that the Earth is not a dead rock we happen to live on. It's a living, breathing, heat-generating system that has been sustaining life for billions of years. Every hot spring, every geyser, every fumarole hissing quietly in a volcanic field, every deep-sea vent glowing in the dark, they are all windows into the same ancient warmth. And now, slowly, carefully, we are learning to open those windows wider. The fire at the center of the world has been burning since before the first fish swam in the first ocean. It will still be burning long after we are gone. But for now, in this brief and remarkable moment, we are here, and we are learning to listen to what the Earth has been quietly offering all along. Somewhere far beneath you right now, the Earth is breathing. Not the way you breathe, quick and light and easy. The Earth breathes slowly. It breathes in the language of heat and stone and time. A single breath might take 1,000,000 years, but it is breathing. It has been breathing since before the first ocean formed, before the first raindrop fell, before the first living thing opened its eyes to a young and glowing world. That breath is the planet's heartbeat. And tonight, you felt it. You learned that the Earth's core reaches temperatures close to 6,000 degrees Celsius, as hot as the surface of the sun. You learned that this heat has two sources: the leftover warmth from when the planet first formed, and the slow, steady decay of radioactive elements deep in the rock. Uranium and thorium and potassium, breaking apart grain by grain, releasing tiny pulses of warmth that have kept this world alive for 4.5 billion years. You learned that this heat moves. It rises through the mantle, that thick, slow-moving layer of rock between the core and the crust, in great rolling currents called convection. The hot rock rises. The cooler rock sinks. And this endless turning is what drives the movement of the tectonic plates, the great puzzle pieces of Earth's surface that carry the continents on their backs. You learned about geysers shooting columns of boiling water into cold mountain air, about hot springs where ancient microbes live in water too hot for any other life to survive, about hydrothermal vents on the ocean floor where superheated water pours out of the seafloor in dark clouds, and whole communities of creatures thrive without ever needing sunlight. Life found a way to love the heat. Life always finds a way. You learned that humans have been finding ways, too. For thousands of years, people have gathered at hot springs to rest and heal. The ancient Romans built bathhouses over geothermal waters. The Maori people of New Zealand cooked food in the ground. And today, entire countries run on the heat beneath their feet. Iceland generates most of its electricity from geothermal power. Kenya lights its cities with steam from the Rift Valley. El Salvador, the Philippines, New Zealand, all of them drawing warmth from the same deep source that has been there all along. You learned that the ground just a few meters below your feet stays at a nearly constant temperature year-round. Not hot enough to boil water, just warm enough to matter. Heat pumps pull that quiet warmth into homes in winter and push heat back into the ground in summer. The earth gives and receives, steady and patient, never asking for anything in return. And you learned that this is not just Earth's story. Io, one of Jupiter's moons, is the most volcanically active place in the solar system, squeezed and heated by Jupiter's enormous gravity. Europa may hold a liquid ocean beneath its icy shell, kept warm by tidal forces. Even the distant moons of Saturn and Uranus may carry geothermal heat in their cores. The warmth that lights this planet's interior is not unique. It is written into the physics of worlds. Everything connects. The iron at the center of the earth is the same iron forged in the heart of a dying star billions of years ago. The heat that warms your home through a geothermal pump is the same heat that drives the plates, builds the mountains, feeds the vents, and keeps the oceans from freezing solid. Nothing is wasted. Nothing is separate. Every system reaches into every other system, and together they make something that works. Right now, the Earth is spinning at about 1,000 miles per hour at the equator. The moon is pulling gently at the oceans, raising and lowering the tides. The mantle is turning slowly in its ancient rhythm. Somewhere, a geyser is building pressure in the dark. Somewhere, a hot spring is glowing faintly in the cold mountain air. Somewhere on the ocean floor, a vent is pouring warm water into the deep, and small creatures are living their whole lives in that warmth, never knowing anything else. And here you are, resting, held by a planet that has never once stopped moving, never once stopped warming the world above it. You are small. The universe is vast. And somehow, in all of that vastness, you landed on a living world, one with a heartbeat you can feel if you get quiet enough. Rest now. The earth has you. Subscribe for a brand new earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.